Hello and welcome back to another deep dive. Today we're opening up the chemistry textbooks, specifically Unit 1 solutions.
It's good to be here.
Now, to be honest, when you first look at this chapter, some parts can feel a bit dry, but there's a topic in here that feels almost like magic.
I know the one you mean. It's the absolute secret weapon of solution chemistry.
So before we get into the heavy definitions, I want to start with a question. This morning, it was freezing outside, and I saw a truck spreading salt on the roads.
Ah, the classic question.
It is. We all know we do this, that salt melts ice. But if you stop and think about it, why? I mean, ice is cold. Salt is just salt. Why does sprinkling a white powder on ice make it turn into water?
And it's not the only place you see it, is it?
No. On the flip side, my grandmother always said, add a pinch of salt to the water to make the pasta cook faster because it boils hotter.
The grandmother wisdom is actually backed by thermodynamics here.
Good to know. But it seems contradictory, doesn't it? In one case, salt melts ice. In the other, it makes boiling water even hotter.
And today, we're going to unpack that. They're not two different things. They are, in fact, the exact same phenomenon.
Okay, so what is this master key we're talking about?
We are unpacking colligative properties and determination of molar mass.
Yay.
And for everyone listening, especially students gearing up for board exams, this isn't just about salting roads.
Right.
This concept is universal. It applies to any non-volatile solute in any solvent. And, historically, before we had fancy sensors, this was the only way for chemists to find out what a mystery substance was.
A detective's tool.
Exactly.
So if I'm a chemist in the 1800s and I find a jar of white powder, this is how I figure out if it's sugar or poison.
Precisely. By dissolving it and measuring how it changes the freezing or boiling point.
I love that. Okay, let's start at ground zero then. The term itself, colligative. It sounds very academic.
It does. It comes from Latin, meaning bound together. But here is the zero-level explanation. At the simplest level, colligative properties depend only on the number of solute particles.
Only on the number, the count.
Just the count, the concentration. It doesn't matter what those particles are. Their identity is completely irrelevant. You could add sugar, you could add urea. If the number of particles is the same, the effect is the same.
Wait, hold on. I have to push back on that a bit. Surely the chemistry matters. I mean, a sugar molecule is big, it's heavy, urea is smaller. You're saying a heavy molecule doesn't change the water more than a light one.
I am so glad you asked that because
Yeah.
that is the #1 misunderstanding. That's where students lose marks.
Okay.
Our intuition says, heavy molecule, big effect. But colligative properties are like a democracy. Every particle gets one vote. It doesn't matter if you are a big protein molecule or a tiny little ion. One particle, one vote.
One particle, one vote. I'm writing that down. So it's about the crowd, not who is in the crowd.
Perfectly put. It is strictly a numbers game.
Why? Why does the mere presence of these particles change how water behaves?
Okay, to understand this, we need to zoom in. I want you to do a little mental exercise. Close your eyes for a second.
Okay, eyes closed.
Imagine you are a single, pure water molecule at the surface of a liquid. It's freezing cold. You are considering, shall I stay liquid or shall I lock myself into that ice crystal nearby?
I am weighing my options.
Right. In pure water, at 0 degrees Celsius, it's an easy choice. You freeze. But now, imagine we add salt. Suddenly, you are surrounded by salt ions. They're buzzing around, bumping into you, distracting you.
Okay, so I'm distracted.
You are. But what's really happening is about entropy, the measure of randomness or chaos.
Right. Nature loves chaos.
Exactly. The salt solution, with water molecules and ions all mixed up, is very chaotic. High entropy, it's like a party. The ice crystal, on the other hand, is very ordered. Low entropy, it's like a boring classroom.
And nature prefers the party to the classroom.
Precisely. The water molecules are so much happier in the chaotic, salty liquid that they resist moving into the boring, organized ice structure.
So to force them to freeze, you have to.
You have to lower the temperature even more. You have to make it so cold that they have no choice but to settle down. And that is why we call it freezing point depression. The freezing point goes down.
That makes so much sense. Is there an analogy that works for this? Something simple to remember for the exam?
Yes. The swimming pool analogy. This usually makes the concept clear for everyone.
Okay, I'm ready.
Picture a calm swimming pool in winter. This is your pure water. When it hits 0 degrees, a smooth sheet of ice forms on top.
Simple enough.
Now, throw 100 swimmers into that pool. These are your solute particles, and they're just splashing around everywhere.
A crowded, chaotic pool.
Exactly. Now, Try to freeze the surface.
Yeah.
The swimmers are constantly breaking it up. They're physically getting in the way of the ice crystals trying to connect. They crowd out the ice.
So the ice can't form a solid sheet because there's always a swimmer in the way.
Correct. So 0 degrees is not cold enough anymore.
Yeah.
You have to lower the temperature to, say, -5 or -10 degrees Celsius to overwhelm their disruption and finally freeze the pool.
And that explains the road salt perfectly. The salt particles are the swimmers.
You've got it. If the air is only -2 degrees, the salty water on the road simply can't freeze.
Yeah.
So the ice melts.
Okay, the concept is clear. But you mentioned earlier this is a detective's tool.
Mhm.
Why does this concept exist? Why is it so important in chemistry?
This goes back to Jacobus van Hoff. He won the very first Nobel Prize in chemistry for this work.
The first one ever. Wow.
Yes. You see, back then, chemists had a huge problem. If you discovered a new white powder, how did you find its molar mass? How big was the molecule?
You couldn't just weigh one molecule.
No. So they used colligative properties. This is why we study it. It was the universal method for finding the molar mass of unknowns.
So how does that work? How do you go from a temperature change to a molar mass?
Well, you take a known mass of your mystery powder, say 10 grams. You dissolve it in a known mass of water. Then you very carefully measure how much the freezing point drops.
Okay, so I see it freezes at -2 degrees instead of 0.
Right. And since that drop depends only on the number of particles, that 2-degree drop tells you exactly how many moles of particles are in the water. The thermometer basically acts like a particle counter.
I see. And if I know the number of moles, and I know I started with 10 grams.
Grams divided by moles gives you molar mass. Case closed.
That is genuinely cool. CSI. Chemistry.
It really is.
Can we do one more visualization? A mental movie inside the beaker?
Of course. Picture a beaker of pure water. A thermometer shows it's at 0 degrees Celsius. You can see delicate ice crystals just starting to form.
Okay, I see it.
Now, visualize adding a spoonful of salt. The salt ions disperse, they surround the water molecules, and they literally pull them away from the ice crystals.
So the existing ice actually melts.
Yes, the equilibrium is broken, and it melts back into liquid. Now you start cooling the beaker. The temperature drops, -1 degree. Still liquid. The salt is keeping things chaotic.
Too distracted to freeze.
-3 degrees. Still liquid. Finally, maybe at -5 degrees, the thermal energy is so low that the water molecules have to settle down, and new ice begins to form.
And that gap from 0 to -5, that's the colligative effect.
That 5-degree difference is your data. That's what you plug into the formula.
Okay, speaking of real life, we talked about salting roads. Where else do we see this?
Well, the most obvious one is in your kitchen. If you boil pure water, a thermometer will read exactly 100 degrees Celsius. But in salty pasta water, it will go higher, maybe 101 or 102.
So my grandmother was right. It does get hotter. But why? With freezing, it was about chaos. What about boiling?
Think of boiling as an escape. Water molecules want to escape the liquid and become vapor. The salt particles act like tiny anchors, holding them back.
So they lower the vapor pressure.
Precisely. To overcome those anchors, you need to add more energy, more heat. So the temperature has to go above 100 degrees to make it boil. We call that boiling point elevation.
Okay, makes sense. What about in cars? Antifreeze in the radiator, is that the same idea?
It is the perfect technology application. We use a substance called ethylene glycol, and it does 2 jobs at once.
2 jobs.
In the winter, it acts as a solute to lower the freezing point. So the water in your engine doesn't freeze and crack the block. It might stay liquid down to -30 degrees Celsius.
And in the summer?
In the summer, in Delhi when it's 45 degrees, that same solute raises the boiling point. So the engine fluid doesn't boil over. It basically makes the liquid range of water much wider.
That's fantastic. So antifreeze is also anti-boil.
Exactly.
I have a question. It feels a bit counterintuitive. You might think adding more stuff to water makes it thicker, so it would be harder to melt, right? Like it should raise the freezing point.
That's a very common thought, but it's where you have to trust the thermodynamics, not your gut feeling about thickness. Remember, it's about entropy.
The chaos.
A solution is more disordered. Nature protects that disordered state. So adding stuff actually makes it fight against becoming an ordered solid. The stuff is an agent of chaos, keeping it liquid.
I see. Okay, we have the concepts. We have the visuals. Now, for the students sitting for their board exams, we need to be exam safe. We need to talk numbers.
Right. Let's get technical. This is where you score the marks.
What are the formulas they absolutely cannot forget?
There are 3 main ones. For boiling point elevation, the formula is delta TB equals KB into M.
Okay, let's unpack that. Delta TB is the temperature change. KB is a constant. What's M?
This is crucial.
Yeah.
M is molality with an L, not molarity.
Okay, this is a huge point. Why does that matter?
This is a favorite Viva question. Molarity is moles per liter. It depends on volume. But when you heat something, its volume changes. It expands. So your molarity would change with temperature.
That sounds very unreliable for an experiment.
It is. But molality is moles per kilogram of solvent. Mass doesn't change with temperature. So for any experiment with temperature changes, you must use molality.
Got it. Molality because mass is temperature independent. Okay, next formula.
For freezing point depression, it's the same structure. Delta TF equals KF into M.
Simple enough. And the third.
Osmotic pressure, usually written as pi. Pi equals I MRT.
Whoa, hold on. We switched to a capital M there.
Yes, for osmotic pressure, we use molarity because it's usually measured at a constant temperature. But did you notice the little I at the start?
Dear I, that's a Van Hoff factor, isn't it?
Yes. And if you forget everything else, remember this. The Van Hoff factor is the biggest trap on the exam.
Why is it a trap?
Remember our rule. One particle, one vote. If you dissolve sugar, one molecule stays as one molecule. So I is 1. But what happens if you dissolve salt, NaCl?
It breaks apart, dissociates into two ions.
Right. One sodium ion, one chloride ion. One particle becomes 2 particles. So your I factor is 2. You have to multiply your concentration by 2.
Because it's a numbers game. If you forget the I, you're only counting half the votes.
Exactly. For any electrolyte, if you forget the I, your numerical will be wrong. You will lose marks.
That is a pro tip. Always ask, does the solute break apart?
Correct.
And finally, just to recap the calculation for molar mass, how does that workflow go?
3 steps. Step 1. Use the delta TF they give you to find the molality. Step 2. Use the definition of molality to find the number of moles.
Ends up 3.
Divide the mass given in the question by the moles you just found. That's your molar mass in grams per mole.
Delta T to molality. Molality to moles. Mass divided by moles. Solid.
It never fails.
Okay, we've covered a lot. Let's do a quick summary for revision before we wrap up.
Good idea. Let's recap. First, the core idea. Colligative properties depend on particle count, not identity. One particle, one vote.
Right. And the analogy to remember, swimmers in a crowded pool preventing the ice from forming.
Real-life application.
Yeah.
Antifreeze in your car working in both winter and summer.
And the key formula, delta T equals K into M. And remember, M is molality.
And finally, the Van Hoff factor. Always check if your solute splits apart. Don't forget the I.
Fantastic. You know, next time I'm boiling water for Maggi noodles, I'm going to look at that bubbling water completely differently. I'll just see the invisible battle. The salt ions holding the water back, entropy fighting against order. It's a whole drama in a pot.
That is the best way to learn chemistry. See the particles in the world around you.
Well, that's all for this deep dive into colligative properties. For everyone listening, master this part of Unit 1. These questions are high-scoring if you just remember to count the particles.
Absolutely. Keep your concepts clear, practice the numericals, and you will score full marks.
Thanks for listening, and we'll catch you in the next deep dive.
Goodbye, and good luck.